Alright, and welcome back to week 2. So today we're talking about annuity investments. Okay? So at some point in your life, pretty much all of you will have an annuity investment to your name. What an annuity investment is a large sum of money. Okay, so a generally $500,000 type large amount, which is used to pay a regular equal payment every period over time. Okay? So examples of this include your superannuation fund or scholarship fund. So what we're talking about here is this large amount of money that you will build up over time, and then at some point will start regularly withdrawing from. Okay? So in order to have this large sum of money to access, we must first build it. Okay, so this annuity doesn't just appear out of nowhere. We do have to build it ourselves. So typically we add a specific amount to the fund periodically to attain the desired value at the end of the term. So at some point in your life, you'll meet with maybe a financial planner and go through, okay, how much do you want to have for retirement? And based on that, that will dictate how much you need to put away now based on when you do want to retire. Okay? So there's a few variables in question here. So in particular, there's time, the rate that you're getting, and then the amount that you want to get in the end, the amount you have to start with. So we've got this lovely little equation. Okay? So this situation you saw in a couple examples in number patterns. So this is a scenario where we start with some amount of money. So you might have, a base of $1,000 to start your annuity. You are regularly accruing interest. So we've got this idea of a geometric growth with interest, which is compounded. And then you also have this regular deposit. So it might be every month you put in $50, $100, $1,000, whatever it might be to get the amount that you want. So this does parallel the combined difference equations that we had a look at. We all remember what that equation looked like. This one's fairly similar. So A is still our variable in question. I'll write out in just a second what each of the variables mean. So A is P times 1 plus R over 100 to the N. So that right there looks like just compound interest. So this part of the equation tells us, okay, how much of the amount in the fund is just from the interest earned on the very initial amount that we deposited. Okay, but it's not just that. We're also going to have plus Q times a lovely little fraction. On the top of the fraction, we will have 1 plus R over 100 to the N. Just 1 second. Minus 1 over R over 100. Okay. So this is what our equation will look like in the end. It's got the two components. So this first component here, okay, is the amount just due to interest on the initial amount. And then this second part, the Q, that's going to be our deposit. This accounts for both the deposit and the interest accrued on the deposits. Okay, so let's write out what each of these variables means. So A, keep our font color, so red, this is very important. A is the final amount in the account. Okay, so that would be same as compound interest. A is what we end up with. P is the principal. Principal, the initial amount. So our newest variable is Q. Q is the regular periodic payment. So it will depend, again, in the future whether you're making this payment weekly, fortnightly, monthly. Those are generally the best options though. Also in the equation we've got N. N is the same as it was with compound interest, so the number of deposits slash compounding periods. Okay, those will be the same. And R, okay, that's your interest rate. I'll be more specific, it's your periodic interest rate. Okay, so again, if the payments and interest are being compounded monthly. We'll take whatever rate you get for the year, divide it by 12. Generally, when we've got these types of questions, the rate at which you're depositing and the rate and the frequency of the compounding periods will be the same. The textbook questions actually don't specify this, but they should. Okay, so if you can choose to make deposits monthly, even though your interest is getting compounded quarterly or weekly, they don't have to be the same in reality. In order to use this equation, however, they do need to be the same. The CAS, however, has lovely little built-in features that allow you to go beyond the restrictions of this equation. Alrighty, so we have this lovely little equation. Let's get to using it. So our first example is that Luke begins to save for retirement. He makes an initial deposit of $1,000 to his super. Okay, so it's never too early to start. Every month thereafter, he makes a deposit of $50 per month. Now that's pretty minimal. Okay, generally you will be expecting to make a much larger deposit than that if you're going monthly. Okay, but just a toy example here. The account earns 3.5% per annum compounded monthly. How much will he have after 40 years? Now again, the textbook stops specifying that it's compounded monthly, or it doesn't specify the frequency of the payments. It assumes they're the same. So it'll just specify one of them, but really they should be specifying both, as I've done here, because they can actually be different. It just means that you can't use our lovely little equation here. So we'll do this one both by hand and on the CAS. So let's just scroll up a little bit. First, we'll just use the equation, fill it in as is, and then we'll use our lovely little finance solver. So as always, I really would like you to be identifying your variables. So our first variable is A. Okay. A would be the amount in the end, which at this point in time we do not have. That's our big question mark. P, however, is our initial deposit, or the initial amount in the account. It's $1,000. Q, that's your periodic deposit or payment. So that's $50. N, okay, the number of payments. Since he's making payments monthly for 40 years, that will be 40 times 12, or 480. Okay, so he's going to have 480 compounding periods and 480 deposits. And finally, R, your periodic interest rate. So because that 3.5% is monthly, we need to divide it by 12. Again, we can just chuck it like that right in the equation. So if we were to do this one by hand, it's going to look something like this. A is equal to 1,000 times 1 plus 3.5 over 12 over 100 to the 480. So that's our first component. Sorry, it looks like a 6. That's the first component of the equation. The second component plus a $50 deposit. One plus 3.5 over 12 over 100 to the 480 minus 1. I'm going to recommend when you put this on your calculator to put another set of brackets around that whole big thing, just in case you're a little messy with where you put your division signs. And then so you can go ahead, put that whole thing into the CAS calculator. Just a little bit messy. And it should evaluate to $56,280.29. Okay. Now that's not a huge amount to retire on, which kind of reiterates what I was saying before. A $50 monthly deposit for retirement is not really going to cut it in our current economic state. So that's doing it by hand, manually entering that exactly on the CAS as I've written it. Now we also have our lovely finance solver. So I've got a blank calculator page to open the finance solver. It's menu 8 and 1, and it will pull up this little pop-up menu. So now I can go through and fill in the values, starting with N. Again, it reiterates at the bottom, that's the number of payments, which we already found was 480. Again, remember to move between the spaces by pressing Tab, not Enter, or the arrow keys. So 480 is our N. I, just to be a little bit different than the equation, is the yearly rate, not the periodic rate, so I do not divide by 12. PV, the present value, okay, the initial amount, that $1,000 that is currently in the account, okay, is going into the account, not in his pocket, not spendable. Makes me sad that it's not spendable, so that's going to be a negative value. Now this is the first time we're actually going to put something in the payment. Now our payment of $50 is happening every month. Okay, it's going out of your pocket, into the bank, not spendable. That will also be negative. Future value, that's what we're looking for, so we'll come back to it. For now we press Tab. That should be 12. When I tab, it will by default update. So this is what I was saying, that even though the equation requires the payments to be the same as the compounding period, the CAS actually allows you to make them different. So you can change one manually. So going back up, tab, 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 to get back to your future value, this is what we're looking for. So I press Enter. And that's the exact same value that you would get by hand if you manually entered the equation. So $56,280.29. Okay. So I will just reiterate here. Okay. Or on the CAS menu, 8.1 to open the finance solver. Okay, really important to remember, PV and PMT must be negative. Okay, so the values, if we do it on the CAS, your N is 480, your PV is negative 1,000. Sorry, the I goes first. Again, your yearly interest rate, just to be different from the equation. The payment is negative 50. The future value this is where you'll come back and press Enter. Your PPY is 12 because it's your payments are monthly, and then your CPY is 12 because your compounding period is monthly. So then this becomes exactly what it does if you enter it by hand. So that's a basic introduction to annuities. Alrighty, so we've done solving for the future value, but we can also solve for any of the other 4 variables. So again, now our equation has 5 variables, so as long as we have 4, we can always find the 5th. So here the scenario is Nada wants to save up $500,000 saved up for her retirement in 45 years. She finds that she can get an interest rate of 4.2% per annum compounded monthly. She currently has $500 to start her annuity. What does her monthly deposit need to be? Okay, so again, always start reading the question. If you're one who likes highlighting the key words, key numbers, but really important to write out what each of the variables is. So Again, Nada wants 500,000 saved up in 45 years. Her interest rate is 4.2% per annum monthly. She currently has $500 to start that annuity, and we want to figure out how much does she need to put in every month in order to accrue $500,000 in 45 years. So the A, that's the future value. Okay, she would like to have $500,000. The P, so what does she have right now? Okay, decent starting point. She's got $500 at present. And next up is our Q. That's a big old question mark. That's what we're looking for. How much does she need to make her regular payment? N, okay, 45 times 12 is 540. So every month she makes a payment, so she makes 12 payments per year for 45 years, for a total of 540 payments so that she makes, and then also compounding periods for interest. And last but not least, the R. Okay, so here again we've got monthly, so it needs to be 4.2 over 12. So in this scenario, if we were to just fill in the equation and type it in on the CAS, unfortunately, because the Q isn't isolated, it's not going to solve for it immediately, so we will need to use solve. So I'm going to do a little bit of magic here like they do on the cooking shows. So I've already got it all set up here. So what we would need to do is solve, comma, 500,000 is equal to P plus 1 plus R, in this case 4.2 over 12 over 100 to the N, which is 540, plus Q times this beautiful looking fraction, 1 plus 4.2 over 12 over 100 to the 540 minus 1, and then in the bottom of the fraction, R over 100. Okay, and then always you need the comma, the variable you're looking for when you're using solve. So hopefully we recognize this isn't overly efficient if you had to type this in every single time you needed to do one of these questions. So I'm going to post another video as well about some tips and tricks on the CAS so you can store formulas just to make it a lot easier. So here I press enter and it tells me Q is $310.57. So that would be how much she would need to pay each month. Okay, as I said, the $50 in the previous example is pretty minimal. This is more the realm of what you're looking at, about $300 a month. So we find that Q is equal to $310.57 per month. Okay, so that's how much she's going to have to deposit every month. Now, as I said, there is a short way to store formulas, but we do also have our good old finance solver we can always use. So, menu 8.1. Okay, so my values from the last example are still there, so we'll just write them over. So our N was 540. Our interest rate, we got a slightly higher rate, okay, 4.2%. Her initial deposit, though, was slightly lower at $500, again, negative, because it's in the bank account, she can't spend it, so that's negative. Payment, that's going to be what we're looking for, so we'll come back to that. Future value, we want 500,000. Again, here it's positive because in those 45 years, basically she can now take out that money and spend at will, okay? And we've got the 12/12 for our PPY and CPY. So we're looking for our payment, so let's press enter. Okay. Notice it is negative, but it's the exact same value, $310.57. Remembering 2 decimal places when you're rounding to cents. Again, the reason it's negative here is because it will be a deposit, so it's coming out of her pocket. It does not mean a negative payment, so your answer will still be positive. Okay. So this is the same on the finance solver. Okay. And your little disclaimers, PV is negative, FV is positive. So those are two examples that really encompass what you can do with annuities. So you've got your two options, whether you want to fill in the formula on a calculator page or use the finance solver to help you. Okay, so again, I'll post another video about so the tips and tricks for entering formulas on the CAS. But for now, okay, if you're feeling that you don't want to watch the tips and tricks, you're looking at 7.6, number 1, 2, and then 4 to 7. Okay, so, and if you have any questions, stop by my office, stop by Extra Help, and we can give you a hand.